All right. So now we're doing SN1 type of reactions, and let us find out what this SN1 type of reactions are all about. SN1, which are also called substitution, nucleophilic, unimolecular. Now, any such reaction would always take place in, just a moment. Yeah, any such reaction would take place in two steps. SN1. Why is it called SN1? Let us find this. See, in many substitution reactions, nucleophilic substitution reactions, especially with tertiary alkyl halides, the substitution takes place in two steps. Now, consider a reaction of any one such tertiary halide. I'm taking tertiary butyl bromide. So if I take up this, this is step number one. In step number one, the bond between carbon and halogen breaks. This is like, halogen taking both the electrons and moving out. You get a carbocation, obviously. So your carbocation formed would be like CH3. And there is this bond going behind. And then there is this bond here. This is CH3. This is also CH3. And here, there is this empty orbital because bromine took away both the electrons and the carbon will have an empty orbital. This empty orbital without any electrons is positive, and we have Br minus moving out. The question is, how did this happen? Where did this molecule get energy for breaking this bond? Now, this molecule got energy from breaking this bond by by solvation of bromine that took place. So bromine undergoes solvation. Some of the bonds would break because of some heat which is liberated, and as these bonds break, Br minus would move out. This Br minus now gets completely solvated. Initially, there is a partial negative charge here. There is this partial negative charge here. And so in any polar and protic solvent, you find that the positive dipoles, right, would approach, positive dipoles of the solvent molecules would approach this, and there would be some solvation taking place here. Now, the positive dipoles coming from the solvent, right, they would start getting attracted towards the negative dipole. And when attraction occurs, there is some heat which is liberated. This heat slowly, is good enough to break these bonds. And as the bond between carbon and bromine breaks, bromine becomes Br minus and moves out. This Br minus now undergoes complete solvation. More energy is liberated. Now that energy is once again utilized by these bonds to break. In short, the energy which is needed for breaking this bond would come from the solvation. And there is this carbocation generated. So when carbocation is one of your intermediates, there are a few things that you have to know here. One, all these all these carbocations, they have a tendency to undergo rearrangement as an impossible. So in this type of substitution reactions, you always find that the molecules may undergo rearrangement, and that's because the intermediates are carbocations. Another important thing, which alkyl halides would preferably undergo SN1? Obviously, those alkyl halides which are able to generate more stable carbocations. Here, tertiary alkyl halides would generate very stable carbocations, and hence, tertiary alkyl halides may undergo SN1 easily. This was step number 1. In step number 2, and remember, this is slow and rate determining. This is slow and rate determining. So now you have to know one thing, that I may put in a few things like the order of reactivity, because this is the slowest step, right? And in slowest step, carbocation is an intermediate. So any alkyl halide which forms a very stable carbocation can undergo this reaction very easily. So we have tertiary greater than secondary greater than primary. This is the reactivity. You also have to know that rearrangements are observed as and when possible. So a few other things like rearrangements are observed. The order of reactivity goes from, tertiary alkyl halides to greater than secondary, greater than primary. Okay, now the second step. The second step is like you start with your carbocation. And you have your CH3 and you have your CH3 here, right? And then you have this positive sign, carbocation. Now, there are two possible ways in which a nucleophile would move in. We're considering the reaction of tertiary butyl bromide with a nucleophile like OH, for example. So we take up OH, which is our nucleophile. We can call this as our nucleophile. And there are two different ways in which it attacks the molecule. It can either attack like this, or it can attack like this, right? Let us call this as path A, and let us call this as path B. So if A occurs, let's say path A, in that case, the molecule would be like this. Because OH comes from the top, you have CH3 going like this, and all the bonds flipping onto the lower side. This is CH3, and this is CH3, right? And if path B occurs, in that case, your OH goes from below. So this is where your OH is, and this is where your, first CH3, and then you have your CH3 and CH3. You can see that path A and path B, the products have exactly opposite configuration. So the product are the same, but you have, opposite configurations. Now, if you would ask me, what is more, what is produced? Is the product A your major product, or is your product B your major product, right? In that case, you may say, there is a 50% possibility of OH occurring OH going from upside, or 50% possibility of OH going from, from the below or the lower side, which means both the configurations are produced in almost equal amounts. So both the configuration are ideally produced in equal amounts. So now, if your product, has a stereo center here, then a racemic mixture is produced. So what do you get? A racemic mixture. Why? Because both the configurations are produced in almost equal amounts. So one of the other key characteristics of SN1 is that SN1 always leads to racemization, or SN1 always gives you a racemic product, right? Because both the configurations are ideally produced in almost equal proportion. Now, one important thing that I have to share here, and you all have to know this. Just a moment, let me put this properly. So yeah, step number 1 and step number 2. Here you may say that both the configurations are produced in equal proportions, so you have a racemic mixture. However, in competitive exams, right, if they ask you what is produced in SN1 reaction, inverted product is one option, retained product is another option, 50% inverted and 50% retained product is the third option, which according to what we have done so far is most likely our answer. But just listen to the fourth option. The fourth option is slightly more inverted product than retained product. That's the fourth option. Now, if a question like this is asked in your board exam, just remember one thing. Your answer would be 50% inversion and 50% retention. However, if you are asked the same question in competitive exam, then you have to say it is not exactly 50% inversion and 50% retention. It is inversion slightly more than retention. So you get almost 50% each, but inverted product is a few percentage more, which means slightly more inversion than the retained product. Now that should be your answer. I would want you to know this because there are questions asked wherein we make mistakes. In your board, it is always 50%, 50%, but in your competitive exam, it is slightly more inversion than retention. That should be your answer. Maybe 55, 56% inversion and the rest retention, something of that order, right? A few percentage more of inversion is always observed, okay? I hope this is clear to you. So one of the other key, important things about SN1 is that you find that racemic mixture is obtained. So both the configurations are produced in almost equal amounts, bracket mark, although inversion is slightly more. Can anyone tell me why would inversion be slightly more? Just think about it. I'm coming back to you. But before that, I just want to show you a few other reactants which may also undergo SN1. Some other reactants which may undergo SN1 predominantly, right, are this is benzyl halide, and because benzyl halide would always generate a benzyl carbocation which is resonance stabilized, and hence they have a tendency to undergo, SN1 also. So we may put this here. This is the cation which is produced from it, right? And then we also have allyl halides, because this is allyl halide, and any allyl halide would also produce a resonance stabilized allyl cation. Again, stabilized by the resonance. One more conceptual clarity is needed here. I did tell you that benzyl and allyl halides may also undergo SN2. That's because I did tell you that there is a beta unsaturation observed, and whenever you have your beta unsaturation, as you can see here, whenever you have beta unsaturation, you always find that SN2 is highly favored. So the question is, what would be more? Or will it be SN2 or will it be SN1? So if I take benzyl halide for any reaction, what do you think? Will it undergo SN1 or will it undergo SN2? How do you figure out that? Now, in such cases, it becomes a little, difficult to answer as such, because both benzyl and allyl halides can undergo SN1 as well as SN2. SN2 because there is beta unsaturation, and beta unsaturation can always stabilize the pentavalent state, right? That is the transition state in which the carbon is pentavalent. That state can be easily stabilized by beta unsaturation, right? That is something which we have already done. The question is, what would happen now? So here, the trick is the solvent. If you have polar and protic solvent, it highly favors SN1. All SN1 reactions have carbocation intermediates, and carbocation intermediates are extremely stabilized by polar protic solvents. So something like water, alcohol, etc., they would favor SN1, whereas polar and aprotic solvent, I've given you the full list of aprotic solvents, polar aprotic solvents. If you take polar aprotic solvent, SN2 is generally favored. So the solvent can do the trick, right? If you want your SN1 to take place, try using polar protic. And if you want SN2 to take place, then try using polar aprotic, right? So this is a small condition which can allow you to manage your reaction according to the mechanism you want. So I hope this is clear to you. And the last part here in SN1 would be in which reactants SN1 cannot happen. In fact, SN1 and SN2 both, they cannot happen in reactants like benzyl halides. Why? Because there are quite a few other reasons also, but one of the reasons that we know is like due to resonance, a partial double bond character is generated. So this is like aryl halide. Then we have vinyl halides. Now, a vinyl halide also has the same situation. right? And this would be like vinyl halide cannot, because of partial double bond character. And the third is like a bridged halide, where you cannot have planarity attained here because it's a bridge structure. So bridged halides. These three substrates or these three halides, they cannot easily undergo neither SN1 nor SN2. Both would be difficult for all of these, right? So I have given you important information about SN1 reaction. I hope you have understood it. And now I'm going back to your doubts. And if you want to ask anything, you can ask. I'm going towards. Can you repeat the question? I am doing that, Palash. But before that, if you have any doubts, please ask. If you have any doubts, please ask. I am there to answer your doubts. I'm there to answer your doubts. You can, put up any question if you want, and I would be able to answer you. So please come up and ask questions if you have. Right? So one thing, why could in SN1 type of reaction, why is it that we observe slightly more of inversion than retention? Can anyone tell me that? Slightly more inversion than retention. Can anyone give me any idea about why this happens? Please, just think and, just think and tell me. Why is it that in such reactions, we get slightly more inverted product than the retained product? Any idea? Just, if not, then I can tell you that. Coming back to this, remember, before the bond breaks here in step number 1, because this is a very slow step. This is a slow step, right? So before this bond breaks here, some nucleophile, although it can be very, very less because there are 3 very bulky groups, right? But some nucleophile, would always connect from backside and give an inverted product. Although it would be very difficult for a nucleophile to enter into, the space between 3 methyl groups. But yes, I'm talking about a few percentage of inversion takes place, before this bond breaks. And that is why overall, before this bond breaks, there is some inversion or some inverted product already formed. Although this is very, very less, but it still happens because some nucleophile is able to get through the space between these 3 and connect with this carbon and release or remove Br. And that is why there is some inversion taking place even before the bond here starts to break properly, right? So that is something which you have to know. Again, coming back to you if you have any doubts. Yeah, there are 2 questions here. Ishika, is it cause of solvent as it depends on solvation or steric hindrance? See, solvent is not as important as the steric hindrance, Ishika, because of the steric hindrance, a nucleophile is not able to get into the space between these 3 big groups here, right? So when you have 3 big groups here in a tertiary alkyl halide, nucleophile is not able to go in. Once again, the bond breaks because the cation which is formed is extremely stable. And therefore, there is bond breaking more preferred than nucleophile going here. And that is why this happens, okay? Solvent again is not very important because you see solvent is important only for such substrates where you have both the possibilities. Their solvent plays a prime role. See, in tertiary substrates, as such, SN2 is going to be very less. So changing the solvent would not make a big difference. It may retard the rate of reaction, but it may not make a very big difference. So obviously, the solvent needed here would be a polar protic solvent, which would, stabilize this carbocation. However, if you say solvent plays a very important role here, yes, to a certain extent, yes, SN1 is favored by polar protic solvent, great. But the tertiary substrate, right, has to undergo SN1 because nucleophile would find it very difficult to reach this carbon. So inversion would take place, but that would be too less, right? So it would not be like a dominant, even if you change the solvent, SN2 cannot happen easily with tertiary substrate, okay? Clear? So anyone else having any doubts? I'll just come to, yeah, Ishika, is it everything? Is it solved for you?
Yes, sir.
Yeah. Okay, I have a check. Okay, yeah, done. So going back to the next, if you don't have any doubts, right? Okay. One thing that I wanted to talk about is like, I can draw a graph. This is the potential energy, and this is the reaction axis. Your reaction would go like this. This is products and this is reactants, and this is the transition state. This would be like SN2. That is just a transition state and nothing else. However, if I have to draw a similar diagram for SN1, okay, from reactant there's this transition state and then there is this intermediate, or we call this as cation, carbocation. This is transition state. So very quickly transition state is reached, but then it falls back into cation. And then we have the next thing. This is where your product is. So when you have one drop here, this indicates there is one intermediate formed, right? There's one intermediate formed, which is so important, right? This is SN1. You may draw this because I have not given this in my notes. Can anyone tell me what is this? Can anyone tell me what has happened here? What does this represent? What does this represent, the third one? Can anyone tell me that? If this is very clear that there are how many intermediates? There are two intermediates, okay? And there are three transition states. All right. Please tell me how this goes. Anyone who can answer this? Two intermediates. Can anyone, two intermediates. I'm coming to that. I still need one more explanation. Oh, Tirth has given me a great answer. Coming back to Tirth. Yeah, Moto 7 also has the same thing. Okay, I'm coming back to you. Great. I'm happy about it. Good thinking. Tirth, I am unmuting you also. Tirth, unmute yourself. Yeah. Tarshini, sorry. Yeah. Tarshini, I have to mute you, and Moto, I have to, unmute you. All right. Now tell me, Tirth, what do you think? What the second intermediate is?
Sir, the second intermediate is more stable. So after rearrangement,
Yes. How do you come to know that it is more stable?
less potential energy.
Less potential energy. So this is higher, this is slightly lower. So basically, first thing, this is where your carbocation is, isn't it?
Yes.
This carbocation once again undergoes rearrangement and generates a more stable carbocation. Yeah. And then
Yes.
this would undergo reaction to form product. Now, coming back to Vaishnavi.
Yes, sir.
Yeah, tell me, what do you think? Anything more than this?
ना सर आज के because જેનું potential energy એટલે પહેલા normal carbocation જે original બન્યું હોય અને પછી rearrangement થાય એટલે એનું potential energy ઓછું થઈ જાય વધારે stable થઈ જાય.
Perfect. And then we have one more transition state, and then there is this rearranged carbocation, yeah, with lower potential energy, right? Barabar?
Yes, sir.
And then this goes on to form a new transition state, and then finally the product. Okay. So this is also SN1, but SN1 reaction involving rearrangement. So I'm putting it as involving rearrangement. And that too, the rearrangement involving only one step in it, right? So I hope you take down all this. So all of y'all, please take down these diagrams if you have to. After which I would be quickly going to SN. Yeah. Amar, I'm admitting you, sir. Please come. Yeah. All right, great. So please draw all this because it is so important. These are the diagrams, right? The energy diagrams for SN2, SN1, and SN1 involving rearrangements, okay? So now we move forward with SNi reaction, okay? But before that, let us go to our notes and let us find out where we are then, right? So I have finished of doing this. Oh, I had to show you the rate also, which I would be doing. Now, some of the nucleophilic substitution reactions that you have, okay? So before we start with that, just coming back to you and just going through your, yeah, I would go back to the thing. Okay, there is one more thing that we have to put down here. I forgot to tell you that the first step is the rate determining step. So this step determines the rate of the entire reaction. And in rate determining step, there is only one component involved. So concentration of alkyl halide is important for deciding the rate of reaction. So what we can have is, here we can put the rate of such a reaction is always proportional to concentration of alkyl halide, or we say rate is equal to K constant. Because rate depends on the concentration of only one component, we say it is a unimolecular reaction, or a reaction for which order is 1. So unimolecular reaction, we can also put it like this. The order of a unimolecular reaction is 1, because order for a bimolecular reaction like SN2 is 2, and here it is 1. So this is also a very important mathematical form which SN1 would exhibit. I hope everything is clear to you, right? So now we move on to the next part. There are some nucleophilic reactions that I have given here. So there is this R, X. X could be chlorine, bromine, or iodine, and it has been replaced by nucleophile. There are several nucleophiles given here, and these nucleophiles are from various sources. For example, the source of OH minus is NaOH, or the source of nucleophile H2O is again water. This is neutral. In sodium alkoxide, the nucleophile is RO. In NaI, the nucleophile is I minus. So we would go through all these nucleophiles one by one. I'm just going to show you how this works. So starting with, let's say, if you take Rx, this is, minus delta, and this is plus delta. And if you use, let's say, NaOH aqueous, in water, OH minus predominantly would act as a nucleophile because it is highly solvated, and in solvated condition, it would generally act as a nucleophile. So here the reaction would go like this. Attach here, this is removed. Don't worry about whether it is SN1 or SN2, but for a simple substrate, it is normally SN2, and we have ROH plus NaX. The source of getting OH is also moist Ag2O. Many a times they put moist Ag2O, right? This is also the same, and so I can put OR, moist Ag2O. It gives you the same thing, right? It can give you, ROH plus AgX. So because there is like, Ag2O, moist Ag2O is actually AgOH. It is silver hydroxide only, right? So if they write moist Ag2O, obviously you have to balance this equation. Don't worry about balancing, just get the right product, right? You can even have Rx reacting with water. Now, reaction with water would be very difficult because water is a very poor nucleophile. And therefore, you may have oxygen moving here and X moving out. And so basically, has anyone moved out or what? Oh, there's someone who's, yeah. So I think we have this, and we have ROH2 plus with only one lone pair plus X minus. Now this X minus can pull out H, and 2 electrons would go back onto R, and we may have ROH plus HX. So with water, the same happens. You can even have RX reacting with NaOR dash. Here the nucleophile is OR minus, and the same thing happens. Now such a reaction is ideally called this is a kind of this reaction in which alkyl halide is made to react with sodium alkoxide. This reaction is called Williamson's ether synthesis. Williamson's ether synthesis. Okay. Yeah. So these are the few reactions. I have given the full table, which is given in your NCERT textbook, and we would go back to that page and discuss out a few things. Now, if you have NaI taken, then I is your nucleophile. It would replace X, and you have Ri. If you take NH3 as your nucleophile, let us see what happens. Right? So Rx plus NH3. There's this lone pair. Poor nucleophile goes like this. This moves out, and we have R NH3. Because lone pair is given by nitrogen, it becomes plus, and you have X minus. Now your X minus is going to pull out hydrogen, and nitrogen would get back the lone pair, and you have R NH2 plus HX. This is a reaction which is observed with ammonia, and if not ammonia, you can take any other derivative of ammonia. Instead of having H3, you can have RNH2 here. So the same thing would follow. In short, you have to remove HX and connect the remaining. You have to remove H. If I have to give you only the disconnection, it goes like this. Only the disconnections. It is Rx plus H in H. And you just have to remove HX, and that gives you your product. R NH2 plus HX. So this is how you get your product. And what I have shown here is the mechanism by which it happens, how lone pair, attacks, and how H is then removed. So I think this is not very difficult. You can very easily do this, right? Coming back to the rest, you can have any such derivatives taken. This is all fine. The question is here, when you have KCN and AgCN, KNO2 and AgNO2, things are different. So I would be discussing more about KCN, AgCN, KNO2, AgNO2. These are very, very important things. So just before that, I would just go back to you to ask you if there's any doubt with you. If you have any doubts, please ask, right? And yeah, I think if you don't have any doubts, I'm continuing with this. Okay. Going back to you. So now, this is like, instead of taking RNH3, if you take RNH2, the reaction would probably go like this: Rx plus R dash. Okay, let us put it like this. A little Rx plus H in Rn. If you have, instead of taking NH3, if you take RNH2, then obviously you will have Rx moving out, and you end up in getting a product which is RNH R or R dash, whatever it is, right? So if you take R dash here, this is going to be R dash. So you can see the product here. If you take R dash NH2, your product is RNH R dash, RNH R dash. All you need to do is remove HX. Clear? In the same way, if you have two R's and only one H, then that H is removed along with X. So it would be like, you can replace this with R, one more R, put a R double dash, and you can have your product would be RN R double dash, what you see here, right? So these are all derivatives of ammonia, and it is very easy to understand how to get products. Very, very simple, right? As I've told you, the problem comes when you have KCN, AgCN, KNO2, and AgNO2. So let us go back and find out what happens here, right? So going back to that, okay, let us understand what this AgCN is all about and KCN. So when you take KCN, you have lone pairs on both carbon and nitrogen. It is an ionic product. Ionic product or ionic compound. Let's say I'm putting ionic compound, sorry. And therefore, when you take Rx and allow it to react with KCN, you already have two options. You already have two options. One, the lone pair of carbon attacks the positive R, or the second option is lone pair of nitrogen attacks the positive R. Now remember, R is, a carbon containing structure. And you know that when one carbon combines with another carbon, the bond formed is very strong and the bond enthalpy is also very high. In short, it is thermodynamically more favorable for carbon to combine with another carbon rather than nitrogen combining with carbon. And hence, of the two, because this is ionic, carbon here combines. And so the reaction goes like this. The product is RC triple bond N. This is a nitrile plus KX. However, if you take RX with AgCN, things are slightly different. AgCN, this is covalent, and so you do not have CN separated. Because of that, carbon doesn't have any lone pair. So now here, it would only be nitrogen which would attack. And so your product would be R in triple bond C plus now. And you have, Ag here plus X minus. In step number 2, because such a substrate cannot be stable if it has charge here. Either this charge has to be removed or the structure should get one negative charge so that the positive and negative charges balance out. So what we have here is this would pull Ag out and the two electrons would settle on carbon, and we have R in triple bond C, where C has a lone pair and a negative charge. This is isonitrile. CN is called embident nucleophile because it has two nucleophilic sites from where electrons can be given. In KCN, carbon gives electrons, whereas in AgCN, it is nitrogen giving electrons. This is important that in first case, you have nitrile as your product, and in second case, you have isonitrile as your product. So please make a note of this. The mechanisms are so important. You have to know this. In what conditions, what would be the product, etc., etc. If you have any doubts here, I would come back to you and ask your doubts. So be ready with your doubts. I'm just coming back to you. Oh, Pavya has gone out. I'm sorry. Pavya, you can be admitted. Yeah. Anyone who has got any doubts here, you can always ask. I am there to answer your doubts. Anyone who has got any doubts, please ask. Did you follow this? You know, this was so important that, you know, if you take KCN, your product would be a nitrile. And if you take AgCN, your product would be an isonitrile. Okay? In the same way, now that this is done, in the same way, I can have Rx, you know, Rx, I can have, you know, being used for reaction with KNO2. Now, this is again ionic compound. And here you find that this is negative, this is positive. Let us understand what NO2 minus looks like. Right? So basically, NO2 minus would look like this. Now, in case the, you know, if you have this ionic compound here, what happens is it is your oxygen which would, you know, attack. So instead of putting it like this, I may even draw the structure like this. So what I can have is my, sorry, and therefore your product would be RONO plus KX. This is called an alkyl nitrite. Once again, you have an imbident nucleophile where there are two sites. One, it is nitrogen with lone pair which can give electrons, and two, it is oxygen with lone pair but a negative charge giving electron. You know that a site with negative charge is always more nucleophilic as compared to the neutral site, and that is why we have this happening. Okay, now going back to the next. If you take AgNO2, so Rx plus Ag O and double bond O. Here, this is a covalent compound. So your oxygen is not free. Now, a neutral oxygen with negative with lone pair and nitrogen with lone pair. Of the two, what is more nucleophilic? As I've told you that you have to consider the electronegativity. Nitrogen is less electronegative, and so it can easily give away electrons like this, and you have your R, and then we have N double bond O, Ag. This is plus and plus X minus. Once again, into this structure, you have either to remove this or generate one negative charge so that both neutralize each other and stabilize. So like this, and this goes like this. R N plus double bond O, now minus, this is called a nitroalkane. Thus, in one, you have alkyl nitrite, in the other, you get a nitroalkane. Again, very, very important to know all this. So you have to actually, you know, go through this properly. I have not given the mechanism in my notes, but you have to know this properly you may take down, I may give you some time to write everything down. So, you know, you may take down everything. And also regarding this, I may also come back to you. Oh, Drishti, you went out. Sorry. Yeah. Any doubts regarding this, you can raise your hand and I am there to answer. So please ask if you have any doubts. Just raise your hands if you have any doubts. I would be there to explain everything. Right? So if you have anything, yeah, I have chat box. Yeah, I can explain the last reaction. What, Palash? You can explain the last reaction. What is it? Can you explain the last reaction? Yeah, that is the same thing, right? What I've done here is, this is KNO2 and this is AgNO2. These are two different sources of nucleophiles. As you can see here, we've taken AgCN and KCN, and now we have KNO2 and AgNO2. In KNO2, the nucleophile, the product is RONO, where oxygen connects, and in AgNO2, nitrogen connects, right? So this is something which you have to know. And so I explained the entire thing right here, that KNO2 is ionic, and hence you have NO2 minus ion reacting as a nucleophile, in which oxygen is negative, so it attacks first, because a negative charge is more nucleophilic here. And here it is the, because this is covalent, right? Oxygen has lone pairs for donating, nitrogen also has lone pair for donating. But a neutral nitrogen is more nucleophilic as compared to a neutral oxygen. So nitrogen connects and we have this, okay? Okay. I hope this is clear to you. Okay. Yeah, Kashish joined in, yes. Now, any other questions you have, I am there to answer. Yeah, if not, then I would go to the next reaction. There are one or two more reactions that you have to know, and I'm coming back to them quickly. Reaction of alkyl halide with an ester, silver salt of carboxylic acid to form an ester. Now here, once again, this nucleophile is like R-COO minus and Ag plus. So your nucleophile is R-COO, it attacks, negative, partially positive, and you have R-COO, R dash plus AgX. This is your ester which is formed. You can also have your Rx getting reacted with, Rx getting reacted with lithium aluminum hydride, for example. Here the nucleophile is H minus. So you may have, your product would be RH, and you have your LIX and ALX3 all separated, and you can have, 4 of them. That's how it is. And you may even have Rx reacting with, R dash M, where M can be a metal. Here, this is plus and minus, but when alkyl group is with metal, it is minus. It is nucleophilic. The same happens when you have, Grignard taken, R dash MgX. Again, even in Grignard, this is minus. So you can have minus connecting here, or you can have, this minus connecting here. In either case, you have the product formed is R and R dash, right? This is your major product. You may have, the rest would be either MX or MgX2, anything, right? Depending on what you start with. If you take R dash M, you get MX, and if you take Grignard, you get MgX2. But yes, these are all different nucleophilic reactions that happen. You have to know this clearly, and I hope this is clear to you all. Coming back to you, yes, Manav has a doubt. Coming back to you. Yes, Manav, tell me.
Sir, doubt નથી પણ sir મારે પેલું બીજું ટ્યુશન છે આજે વિજય વોરા સરનું, તો સર હું જઈ શકું?
હા, જે લોકોને વિજય વોરાનું હોય એ લોકો જઈ શકો ને. હવે ઘણું બધું થઈ ગયું. નેક્સ્ટ તમે મંડે થર્સડેમાં આવશો એટલે તો વાંધો નહીં આવે.
ઓકે સર.
ઓકે, યા. Achira, you all, if you have to leave, you can leave, right? I think who else, I don't know, but those who have to go, you can go, please. Okay, done. So if you have to go at 5, you can leave at 5. Till then, enjoy chemistry. What else? Yeah. It is like, this is kind of, yeah. Let us go back to the work, right? So this is done. Now we go to SNi. Now there are certain reactions. See, SNi is not a part of our textbook. So you may avoid this if you have to do only textbook, right? You may not do this. So people like Ishika, if you have to do only textbook, you can avoid this, but I can show you this reaction, SNi reaction. See, there are certain reactions which occur in a single step. There are certain substitution reactions which occur in a single step. And you might think, oh, single step, it should be SN2. If it is SN2, then the configuration should be inverted. However, there are certain reactions which occur in single step, but the configuration is 100% retained. So this is not SN2. This is not SN2, this is something else. So one of the possible reactions that can be here is SNi. So when certain reactions occur in single steps, and if there is retention in configuration observed, then obviously they go through a different mechanism. The mechanism is called SNi mechanism. Quickly going through SNi, look at this. Substitution nucleophilic internal. Okay. So let us find out what this is. Normally, when you take up some primary alkyl halides, I have taken up something here. Sorry. I have taken up something here where you start with an alcohol. So this is not really an alkyl halide, but it is a kind of substitution reaction, and that is why I have taken up. This is an alcohol here. So we would be starting with alcohol, and let's say this is R, and then we have this CH2, and then we have this OH. And this is thionyl chloride. Thionyl chloride is S double bond O, Cl and Cl. You know that this sulfur has this big problem with 2 chlorines and 1 oxygen. It is highly electron deficient. And because it is highly electron deficient, what happens is the electrons would shoot here. They're pulled here because it acts as a electrophilic center here. And so the nucleophile would move in. And you have R, CH2, OH plus. And then we have this S, O minus. The pi bond always collapses first. And then we have this Cl. And now we have this, you know, very quickly in one step I can show you. This always comes back and reforms the pi bond. And then there is this chlorine moving out. So you find that there is R, CH2, OH plus, and then you have RS double bond O and Cl, and plus Cl minus, the one which moves out. Now this Cl minus would act as a base, pull your hydrogen back, and you have your structure R, CH2, O, and then we have this S double bond O, and you have Cl. Sorry. So you have this Cl coming in. Now remember one thing, I can draw this a little better. Just a moment. R, CH2, O, S, S, now here this is what you get, but here you find that H is gone, so you have SOCl connected here. Now this bond here is almost like, you know, half broken, half formed, and is quite ionic in nature. So what you can have is, I can show that this is like, you know, partially negative, and this is partially positive, almost positive and negative, full positive, full negative also you can write. So electrons of this bond would, you can even put it like this. I'm sorry, I can directly put it as, you know, this is O minus and CH2 plus. There's a kind of ionic bonding, right, which is observed. So yeah. So now what happens is, from the same phase, Cl enters here, and this would come over here, which means you have R, CH2Cl, and SO2. Because Cl comes from the same side, right, the configuration remains as it is, and that is why it is called SNi, right? All of this would take place in a single step, right? So it is SNi, and you know, your chlorine comes in from the same side. That is why configuration will not change. I have shown this mechanism here, I think here. As you can see that, you know, you have your, you know, the bond between carbon and oxygen is almost ionic. And so, you know, You can have partial or full charges, doesn't matter. It is always in form of an ion pair, as I've written. This is positive ion, this is negative ion. So electron density shifts here to form SO2, and Cl moves here from the same side. So you started with this configuration and you end up in the same configuration. So this is the mechanism, and because chlorine attacks from the same side, right, the configuration never changes. So in spite of taking place in one step, you might think that because it takes place in one step, it should be SN2 and configuration should be inverted. But in spite of taking place in one step, you find that the configuration is retained. The reaction is SNi. Okay, so I think coming back to you and asking you for your doubts if you have any. So if you have any doubts, please tell me. I can solve your doubts. I hope you followed this. See, you can ask your questions if you have, right? So I would be answering your questions if you have any. So if not, then I can. Okay. So if not, then I can, move to the next thing. If not, then yes, we go to the next part. The next thing that we have to do is like the last type of substitution. These are called SNAr, substitution. Nucleophilic and aromatic. Now these are some of the most difficult, reactions. See, we're talking about a reaction in which we carry out nucleophilic substitution on a normal aryl halide. Previously, I have already given you that aryl halides cannot easily undergo SN1 or SN2 because of this partial double bond character. Yes, it is correct, but it may show some reactivity only under very, very extreme conditions. So suppose I take chlorobenzene and suppose I take NaOH aqueous, where my nucleophile is OH, and if I want to react, my conditions, look at the conditions that I have to keep. 623 Kelvin's temperature, 300 atm pressure, so difficult. And you find that your and then in step number 2, you also have to, acidify. After acidification, your product would be OH, a phenol. This is a good example of SNAr reaction, where you find that your nucleophile OH, it attacked aromatic halide and replaced chlorine. One of the things is, if you look at the reaction, the conditions are so extreme that it would be very difficult to perform such reactions. So the question is, why are such reactions so difficult? And they say that there are 4 important reasons why these reactions are so difficult. 1, the first reason why such reactions are so difficult is the fact that the resonance between lone pair of halogen and pi bond in ring. This is the first case, first reason, right? Now you can see the resonance. If you take any halogen like chlorine here, you find that because of which there is a partial double bond character generated between carbon and halogen bond. And it is because of this that it is very difficult to break. This is one important reason why a partial double bond character would not allow the bond between carbon and halogen to break easily. You can draw the resonating forms. The second reason that you can give is the hybridization. Compare the hybridization here. This is carbon with sp2. Now you know that sp2 carbon is more electronegative. sp2 carbon is more electronegative. Because sp2 carbon is more electronegative, you find that it cannot easily shift electrons onto chlorine. Again, because here the S character is more as compared to sp3, S character is more, and if S character is more in any hybrid orbital, it is always smaller. So another important thing is this bond is also very small. So smaller bonds are more difficult to break. And again, this carbon would not shift electrons easily onto chlorine because it itself is also more electronegative. So shorter bond, they say that CCl bond here is about 169 picometers, whereas the normal CCl, where carbon is sp3, is about 177 picometers as given in our books. So, this bond here is always very small, and smaller bonds are always very difficult to break. So the second important reason is it is a small bond and hence it is very difficult to break. Third, suppose if we take this for SN1 reaction, then the first step would be breaking of carbon halogen bond to form a cation. This is a phenyl cation which may be formed in SN1, and this is extremely unstable. So it would not be formed. And because it may not be formed, SN1 is out of question. So the third reason would be instability of phenyl cation, and hence SN1 reaction cannot take place, right? And the fourth point that you have to mention here, I may make this a little smaller. Yeah, and now we have the third point. Fourth point. The fourth point is electron-rich aromatic ring. Electron-rich arene. Now, the arenes are so electron-rich that a nucleophile would not find it easy to come over from backside and attack the carbon. So if a nucleophile has to do a backside attack, right, or if a nucleophile will have to go close to this carbon here for SN2, it would be very difficult because it has to move over a very, very electron-rich ring. Now, nucleophile itself is also negative. The ring also has, ring also is rich in electrons. So they too would repel each other, and nucleophile would find it very difficult to reach this carbon. So all these 4 reasons would make such reactions extremely difficult, right? So let us summarize all these 4 reasons. 1, the halogen, when attached to an aromatic ring, will have a partial double bond character due to resonance, and that would make it difficult for the bond to break. Second, the carbon to which halogen is attached is sp2 hybridized, and sp2 hybrid carbon is more electronegative, and hence the bond between carbon and halogen would get shorter, and as it gets shorter, it is always difficult to break. The third reason being, if you try to perform SN1 on aryl halide, the intermediate would be a phenyl cation, and phenyl cation is extremely unstable and hence not formed. So obviously SN1 is out of question. In SN2 reaction, the nucleophile will have to pass over the electron-rich arene for a backside attack. And it would be very difficult for nucleophile to do that because nucleophile itself is rich in electrons. The ring is also rich in electrons. They too would repel each other, and hence nucleophile would find it extremely difficult to move over the ring and reach this carbon. Okay, so this is about it, and these are the 4 reasons, right? So let us go back to the notes, and I have properly written all of them here, and you can go through all of them. This is like perfect, and this is one reaction that I showed you. It happens with a lot of difficulty, right? So now the next thing is what changes we could make. What changes we could make for such reactions to actually occur on aromatic rings. So if you still want to carry out such reactions, what modifications you would need? One simple answer would be the reaction could go easily if you decrease the electron density of the ring. So if you somehow decrease the electron density of the ring, you probably can carry out such reactions more readily. And this actually happened, and you will have to remember these things properly, that the electron density could be reduced by putting some electron withdrawing groups onto the ring. Now let us see what would happen to the reaction conditions when the same reaction is carried out, but after putting some electron withdrawing groups onto the ring. Let us see what happens. So we are using a nitro group, which is a very strong electron withdrawing group. We're putting it in ortho and para positions to find out what happens to the reactivity, what happens to the conditions. Let us monitor that, right? Okay. So going back to this, you can see that I have placed one nitro group in para position, and look at the conditions now. 443, initially it was 623 kelvins, and now the temperature drops to 443 kelvins, and the reaction happens. You put one more in ortho position, and the temperature again drops down to 368 kelvins, right? And this is again phenomenally low. 368 is even less than 100 degrees Celsius. So it is like about 95 degrees Celsius or so. So that's like, you can do the reaction below 100 degrees Celsius, and you have the product. And the last one is a total surprise. If you have all the 3 positions occupied with nitro, you find that you don't even need a very strong nucleophile. You just take warm water, right, and put warm water into it, and Cl is replaced. You can see that there is an enhanced effect on reactivity if you put electron withdrawing groups onto that ring. Now, it has been observed that putting an electron withdrawing group in ortho and para positions is useful, and it can alter the reactivity to a large extent. However, if an electron withdrawing group is placed in meta positions, its effect on reactivity is not so high. In other words, putting an electron withdrawing group in meta position does not affect the reactivity that much. Now here, we will have to know why an electron withdrawing group in meta position cannot alter the reactivity to a large extent, whereas an electron withdrawing group in ortho and para can actually increase the reactivity to a large extent. So why is it that ortho and para position, the electron withdrawing group can enhance the reactivity, whereas the same electron withdrawing group in meta position cannot alter the reactivity to a large extent? Now that is something which we have to know. Okay, so let us take up that. Here, as I've written here, effect of increase in reactivity is observed only when nitro group is in ortho or para position. A nitro group in meta position does not alter the reactivity as much. This is due to the fact that a nitro group in ortho and para position can withdraw electron density from the ring, while a nitro in meta cannot easily do that. I've drawn all of this here, right? But I'm going to show you how to draw this. So this is for your notes. I'm going back to how we can draw such structures. Pay attention and let us interpret why this happens, because they would be asking you to draw such structures and answer such questions. All right. Let us take up a nitro would look like this. And there is this chlorine. You have your nucleophile. Nucleophile attaches here, and this bond moves here. And there is this unstable intermediate generated. Pay attention. Now, due to resonance, you can see that lone pair and pi bond are conjugated. Conjugation brings in resonance, so lone pair becomes a pi bond becomes a lone pair. You can see this now. Now, this is the key point. Here you have a lone pair, and this is where your nitro group is attached. So now what happens is the lone pair can be pulled out of the ring. And how is this done? This can be easily done here, as you can see. This moves out and this goes here. So you may have one more resonating form generated, which takes the electron pair out. And we have so your ring actually loses electrons. Your ring actually has electrons going out of it. And that is the reason why, if you have your nitro group in meta position, it can take the lone pair out. Although you can continue with this, you can continue with this now. you know, after, you know, you can have your lone pair coming here and this going back here. So from here on, you can also have lone pair becoming pi bond and pi bond lone pair, and it continues. And finally, from here on, chlorine is, you know, taken off and OH occupies. So what you can have here is now furthermore, this comes here and this moves out and you have your product. So this is like putting a nitro in para position. The key step here is this, where electrons are taken out of the ring. And this is what happens when you have your nitro in para position, right? Now let us try putting structures when nitro is in ortho position. Let us try doing that, right? Try putting nitro in ortho and checking out the same. Before that, I'm just coming back to you to, you know, to answer your queries. So if you have any queries, you can, oh, there's something. Shiti says, sir, it would react with all aryl halides. Yes, Shiti, the reactivity would be, you know, difficult, less, but yes, it would happen with all aryl halides. Fluorine, the reaction would be very, very difficult. So we keep fluorine out of it, but chlorine, bromine, or iodine, yes. Okay. Kailash, I have recorded the whole thing. So yeah. Okay, you can come back again. So Shiti, does that answer your question? Yeah. Okay. So we go back to our work. So I hope you have all understood that. Going back to, let us check out with the ortho position. See, you have to be very good in drawing these structures. So as and when you have time, you just start drawing these structures. I'm putting ortho nitro. You have your OH minus coming in, and you can see that this moves in. Look at this. So directly you have OH, you have Cl, and you have this nitro, and you have your. Now this is very simple to understand that this is going to be pulled out of the ring, because again, just as you have nitro in para position, suppose if you had your nitro in para position, the lone pair gets exactly located on para position. So having nitro in para and getting lone pair in para position would take it out through resonance. In the same way, having nitro in ortho and getting lone pair in ortho position would take it out of the ring. So even ortho nitro is good in taking electrons out of the ring and decreasing the electron density of the ring. On the other hand, so I'm not completing this, you can go through the notes, but let us check out with the meta thing, so which is so important. If you have a nitro group in meta position, let us do the same. Let's see let's see what happens. And sorry, we can have OH and Cl, and you have N double bond O, O minus, N plus, and there is this lone pair, and you have this. The next step would be lone pair becomes a pi bond becomes a lone pair. Look at, closely observe the structures now. Your OH and Cl, you have a lone pair here now. And now the lone pair would move on to this next position. Now here, you never have your lone pair settled in meta position. And because it doesn't settle in meta position, there is no possibility of lone pair going out due to nitro group. See, in ortho position, the lone pair is able to move out due to nitro position because lone pair and pi bond of nitro group are conjugated. Lone pair gets settled exactly in ortho position. Here, the lone pair also gets settled in para position, so a para nitro can also take it out. However, a meta nitro cannot take it out because lone pair, in none of the structures, lone pair is settled, in meta position. And that is the reason why a meta nitro cannot decrease the electron density of the ring and to a large extent, and hence it does not affect the reactivity. I hope you have understood this. So coming back to you and asking you for your doubts, if you have any, please tell me if you have any doubts. I'm there to answer your doubts. So if you have any doubts, please ask. If not, then I start with the basics of elimination. Yeah. Ananya has a doubt? Okay. Ananya, coming to you. Yes, beta. Tell me.
સર તમે જે લાસ્ટ સ્ટેપ ની પહેલા જે સ્ટેપ કર્યો ને ખબર ના પડી.
બોલો.
પેલું જે શિફ્ટ થયું ને
અહીંયાથી અહીંયા આવ્યા એ ખબર પડી ઓર્થો વાળું. બરાબર. પછી મેં મેટાનું બતાવ્યું. Nitro in meta position. So OH nucleophile attacking, lone pair is here now, right? This lone pair and this pi bond are conjugated, so lone pair becomes a pi bond. So here you have a pi bond and pi bond becomes a lone pair. So you have this.
Okay.
And this going further. In no case you have your lone pair coming over here. And because lone pair doesn't move over here, it cannot be pulled out. Okay. So nitro in meta position cannot really increase the electron density of the ring. That is what it means. Okay.
Okay.
Yeah. See, all of y'all should be able to draw these resonating structures. Yeah, I have a doubt from someone. Is there a test for us? Yes, beta. From 7 onwards, and those who are not able to give at 7, it is fine if they give tomorrow. I would be keeping the paper till tomorrow, so don't worry. Tomorrow or day after, I think Tuesday would be the last day. So for some, I would be sending the paper even on Tuesday. So, but just be honest in giving the test. Online test, once again, I would have all the topics till substitution, and that would be in the second half of next week. Second half of next week, we will have one more online test. That would be only for Chemicafe, not all 3 subjects. A Chemicafe test next week, second half. Or only for biology? No, today you will have a math paper as well. Set theory. See, today the test that you have to give is, we would be sending you the paper, but next week, the test I'm going to take up is an online test. Okay. Yeah, Ishika has a doubt. Yeah, Ishika, please tell me.
તમે જે નેક્સ્ટ વીક ઓનલાઈન ની ટેસ્ટ લેવાનો છો એમાં પ્રોપર્ટીઝ હશે એટલે આ વીક મારે નહીં આપવાની કે આપવાની
ના આ પ્રોપર્ટીઝ ને બધું નેક્સ્ટ વીક સેકન્ડ હાફ માં જે ટેસ્ટ
હા કારણ કે આજે ખતમ કર્યું એટલે નેક્સ્ટ વીક હશે ને
નેક્સ્ટ વીક માં આખું છે છેક સુધીનું all that we have done all that we do till Sunday is going to be included.
એટલે આજે competitive exams નું છે ને?
હા, આજે competitive છે.
સારું. Okay, thank you.
Yeah. All right. Let us go towards the next part. See, the next part is I have given some more nucleophilic reactions wherein you have chlorobenzene getting converted into benzonitrile by taking CuCN in presence of pyridine at 200 degrees Celsius. The same temperature aqueous NH3 in presence of Cu2O can give you aniline. So these two are, you know, some extra reactions which are also the same, you know, that is why I've given them here. Okay, we move on to elimination reactions. What is an elimination reaction? In any elimination reaction, two atoms or two groups are removed and there is one pi bond which is formed, a new pi bond which is formed. So in a way, elimination involves breaking up of two sigma bonds of the substrate and formation of a new pi bond in a substrate. So the substrate will have two sigma bonds broken and one new pi bond formed. Here, the elimination reactions can be of three basic types: alpha elimination, beta elimination, and gamma elimination. So our textbook has given a simple beta elimination. Again, I would be talking about alpha elimination, but not now. So I have written in alpha elimination, both the leaving groups or both the groups or both the atoms, they are removed from the same carbon. So when you have both the atoms or both the groups removed from the same carbon, the elimination is called alpha elimination. Whereas in beta elimination, generally hydrogen is eliminated from beta carbon and halogen gets eliminated from alpha carbon. And they can be of three types: E2, E1, and even CB. This is very similar to SN2 and SN1, as in you have E2, right, which is very similar to SN2, where the process takes place in one step, E1, where the process takes place in two steps. We do not have a lot of E1 or even CB included, although I would be giving you information about E1 and even CB again. But more often you'll have to know what E2 is, because that is something which we have in our syllabus, right? Okay. So let us take up this E2 elimination, the initial part. So E2 elimination. In E2 elimination, first of all, it is a process in which it takes place in only one step. So it is one step process. It is a type of beta elimination, right? Leaving groups. Pankti lost connection. I'm just coming back to you. Yeah, please come in, Pankti. Yeah. So the leaving groups are, you know, they are in same plane. But in anti-arrangement. they are in same plane but in NT arrangement. Eliminations are generally favored by bases. So if you have, like, I'll tell you how this goes. Let's say this is our I'm putting ethyl bromide. The NT arrangement in same plane would be something like this. This would be like, two of them are NT as well as in, they are in same plane. You can see that the elimination is from staggered conformer. You can see that the bonds are staggered, and you have H, on a normal bond above, and PR is on a normal bond below. So this is NT arrangement, right? And now you have your base, which can be something like OH. In alcohol, if you take OH, it would act as a base, and it would try to pull this. Now there is this one-step concerted process. So what happens is, now this bond is on the verge of getting broken. This bond is on the verge of getting formed. Here you have, generation of pi bond has begun, and the leaving group, which is Br, is going to leave. So all these bonds, which are either half broken or half formed, are shown by dotted lines. And here the actual process would be, this would move here, and the leaving group would leave. This is just an intermediate generated. And then finally, you have your product, C double bond C, and you have H, H, and H, plus H2O plus PR minus. This is, E2 elimination. You can see that there is a transition state involved, right? The bonds which are on the verge of getting formed, or the bonds which are on the verge of getting broken, are shown by dots. And this would give you an alkene. See, here in this alkene, geometrical isomerism is not possible. But if geometrical isomerism would have been possible in this alkene, then there would be trans alkene, which would be formed as a major product. In every such E2 elimination, trans alkene is your major product. So you don't have to worry about anything. Generally it is trans alkene which is formed as a major product. Okay, so this is also in such simple processes, and you can see that it's a one step, and the leaving groups are all in the same plane but in anti-arrangement to each other. I hope you have understood this. There are no rearrangements observed because it's a single step process, and I would be talking more about E2 in my next lecture. I have started with E2, but I would be talking more about all these eliminations next time. So we would more or less finish off the chapter with a few things left towards the end to be done on Sunday. Otherwise, more or less, the chapter would get over. So I would continue with E2 next time. Coming back to you for asking if you have any doubts in E2. So if you have to ask anything in E2, please ask. Yes, coming back to you. Actually, do we have to write answers on paper for the test? Yes, Shaili, for this time, yes. Yes. We would very quickly start with the online thing, but as of now, it would be on, on paper. I would be, giving you an online test once again, and if this online test goes on well, I think slowly even PathMaker would move on to online tests. Just remember, for our test, you all have your passwords and everything, and remember one thing, that if you are working on iOS, please please go through Google Chrome, because iOS is not easily supported. So we go through Google Chrome. So try to enter the platform through Google Chrome, right? chemicafe.winual.com, but put it on a Google Chrome and then enter. That would be easier. Okay. All of y'all, if you still have anything to ask, please ask. I'm here. But otherwise, we would stop here till next time, Saturday. I hope you've understood this properly. I have a lot of examples taken. So next time in elimination, we would have a lot of examples being taken up. Okay. So if you have any doubts, please ask. Otherwise, I say goodbye to you, and we meet next time. Okay. Goodbye all to all of y'all. We meet next time. Okay.